Hi everyone, this is Dr. Swaminathan SM. I am going to discuss about the topic called Nyquist Stability Criterion, that is the problem. So last class we discussed about the Nyquist Stability Criterion condition. So now we will discuss about the problem. So first we discussed about the problems in the last class. Now we will discuss about the problem. So look at this problem. Sketch the Nyquist plot for the transfer function g h of s equal to 1 divided by s into s plus 1. So representing its a frequency response. So just to substitute the value s is equal to j omega. Then you can find the magnitude, that is called the modulus of g h of j omega. So in terms of s, you just substitute the value j omega. So the things are remained for the control system. First one, if the t domain is converted into s domain, means using the Laplace transform. So t is converted into s domain using Laplace transform. Again, s domain is converted into frequency domain, means using the formula called s is equal to j omega substitution. So if you are substituting the value s is equal to j omega, then s domain is converted into frequency domain. Then you can find the magnitude modulus of g h of j omega 1 divided by omega. Omega means that is the first thing, j omega. So you can get, and root of omega square plus 1. So root of a square plus b square. The phase of the gh of omega, that is given by pi, that is modulus phase of gh of 0. So you can get minus 90 degree, that is 1 divided by, that means minus 90 degree, that is s means 90 degree. If s square means that is 180 degree, please remember that. So here this is minus 90 degree minus tan inverse b by a. So here the b is nothing but j omega, that is omega divided by a is nothing but 1. So omega divided by 1, that is called magnitude, that is phase. And next, point 1, to start the plot when omega is equal to 0, then you substitute the value 1 divided by 0, root of 0 plus 1. So look at this previous one, just to substitute the value omega is equal to 0. Then pi is equal to gh of 0, that is minus 90 degree minus tan inverse 0 by 1, that is minus 90 degree. At the end point, omega is equal to infinite. So you can get the infinite root of infinite plus 1, that is equal to 0. And pi, that is the phase angle, that is g h of infinite minus 90 degree minus tan inverse infinite divided by p. So minus 90 degree minus 90 degree, that is 180 degree. So you can tabulate modulus and phase, that is infinite 0 and minus 90 degree 180 degree. You can draw based on this plot. So look at this graph, real time of gh and the imaginary part of gh, then you can get the events, that is omega is equal to 0 means that is infinite and minus 90 degree, and omega is equal to infinite means that is 0 and minus 180 degree. That is the polar plot you can get. So it's a simple activity. You can make the connections, that you start from the word control systems, then start from the s. So these are the small activity. So following the activity, you can make the sketch the Nyquist plot for the following transfer function and check the stability. So Nyquist or polar plot you can draw. You can make this real GH and imaginary part of GH, then it is increased. And Nyquist plot means just reverse, that is a mirror image of the polar plot, that is called the Nyquist plot. So you can get this axis, imaginary axis and real axis. So the region to the right hand contour has been shaded. So clearly you can say minus 1, 0 is not in the shaded region. Therefore, it is enclosed by the contour, and so n less than or equal to 0. The poles of gh of s are at s is equal to 0, s is equal to minus 1, neither at which are in the right hand side of the plane RHP, then P naught is equal to 0. So n is equal to minus P naught equal to 0. So the system is absolutely stable. So you can find whether the system is stable or not using this function. And the stability conditions, that in examining the stability of the linear control system using this Nyquist stability criterion conditions, the three possibilities can occur. First one, there is no encirclement of the minus 1 plus j 0 point. It implicates that the system is stable. That is, if there are no poles of g h of s in the right half of the plane, otherwise the system is unstable. That is the first condition. And the second condition means there are one or more counterclockwise encirclements of these minus 1 plus j 0 point. In this case of the system is stable if the number of counterclockwise encirclements is the same as the number of holes GHS in the right hand side of the S plane. So otherwise, the system is called unstable. So there are one or more counterclockwise, that is clockwise encirclements of the minus 1 plus j 0 point. In this case, the system is said to be unstable. So these are all the Nyquist stability criterion conditions. Thank you.